Is there anything in there anyone wants me to go over? Cure it. Number 7? Okay, so that's this guy down here. A net force of 6.6 newtons acts on a 9 kilogram hamster, as a big hamster. If this object accelerates from rest to 3 meters per second west, A, how far did the hamster travel? And B, what was the time of the acceleration? So, this one is, it's a kinematics question and they don't give us enough information. So we want to know how far this thing traveled. So good practice is to fill out, the chart of everything we know. We want to know how far it went. We know that it initially was at rest. We know that finally it was going 3 meters per second. We're told that this thing is accelerating, but we don't know what the acceleration is. What we are told, though, is that there is a net force acting on this thing, and we also know the mass of the hamster. So we know that the net force is 6.6 newtons, and we know that the mass of the hamster is 9 kilograms. So, using this information, that F net equals ma, we can find the acceleration, insert it into here, and then do our kinematic equation to find out the distance, and then the same thing down here for the time. You want me to keep going? Okay. Anybody else want me to take a look at anything I assigned over the weekend for homework? We're good. It was easy, relatively speaking. Cool. It was either easy or we didn't look at it. Love it. So flip back to this page here. This is what I was hoping we would have been able to get through as well on Friday, but we did not, and that's okay. So free body diagrams. I vaguely introduced the concept of free body diagrams back when we were, don't flip back, I'll flip back. Looking here, looking at Newton's second law, F net equals ma, and then we were drawing a bunch of stuff. Before in kinematics, drawing was recommended. Now you absolutely have to do it in the form of what's called a free body diagram. So before we actually, we've done a bunch of these already. This is just more practice in it, formalizing what I want to see you guys do. Before we do that, I'm going to list here some of the forces that you're typically going to see and when they're used. So we've talked about a few already. Fg was the first one I think we introduced. Fg is what? Sorry? Force of gravity. And we know that Fg is equal to the mass of the object times little g, and little g is gravitational field strength. This value, little g, is going to change depending on where you are. If you're really high above the Earth, it's going to be different than if you were like right at the Earth's surface, or if you were on the moon or Jupiter. This little g here can change to be a whole bunch of different things. The next one that we looked at was Fn. And that guy is what? It's the normal force.
You have to write it with the N like that when you write normal force?
As opposed to what?
No, I mean like the N, like you have your N kind of like in italicized sort of.
These are all, so like the G here, the N here, I don't mean to slant it, I do mean to subscript it though, like typically it's written a little bit lower, like it's not in line.
No, I mean in your description, under the description part, you have your N.
Oh, that's just how I write.
Okay.
That's just my printing. I mean, a reasonable question. Normal force is a supportive force. And it's, I don't have a lot of space. It's always perpendicular, that's the mathematical symbol for perpendicular. To a, and I'm running out of space here, but that should say surface. The next one we've got here, did we address any other ones? We did. Two more. The next one that we addressed, if I'm not mistaken, was sometimes just F big A, or sometimes it's written as F little a. Sometimes it's written as FAPP. This is an applied force. An applied force is just a generic push or pull. If you can't call it anything better, we just call it F applied. It doesn't really matter, this particular force, but it gets used, so we'll address it. The next one we talked about was this guy here, F sub lowercase f. What was that guy? The force of friction. And the force of friction opposes motion. Generally. For a sliding object, it opposes motion. For a rolling object, friction is a particular kind of friction is actually responsible for propelling you forward. What else we got here? We've got, which one haven't I addressed? This one. Sometimes it's called F big T. Other times it's just called big T, which is weird because another thing that we're going to talk about that's big T. So I don't really like to use this one. I usually write it like this. But this is a tension force, or force of tension. And tension is going to be found where? Believe it or not, no. Elastics are just springs. Rope, there you go. And tension is found everywhere along the rope. I'll just write everywhere along. We're going to get into some of these in more detail. We're going to talk about force of friction in more detail, how it's calculated. We're going to talk about force of tension in more detail, how it's applied. At this point, I'm just introducing them. We've got another one here, Fe, big E, and F sub big E is what? Yes, what Manuel was just describing that happens in springs and elastics. This is elastic force. Springs, elastics, that kind of thing. Again, we'll get into that, how that one is calculated in more detail coming up here too. And then the last one, this one is just F sub air, which makes it look like the word fair, but it's not. This is just air resistance, which is similar in some respects to friction, but in other respects fairly different. Friction is just resistive force between two rubbing objects. Air resistance is the resistance of air pushing back on another moving object. Similar in how they both oppose motion, but different in how they're actually calculated. Force of friction is really easy. We'll do it in this class. Air resistance, really, really hard. I've never actually done it. It'll be reserved for engineering classes in university, assuming you need to know how to do it. Because it takes into account things like the material the object is made of, the shape the object has, its surface area, there's a few different things, but actually calculating air resistance is really quite difficult. So for the sake of free body diagrams, on FBD, I'll just rewrite this here as a free body diagram. So for a free body diagram of any object, it's a diagram that labels all forces acting. And only the forces. So if I've got a book being pushed across a rough floor at constant velocity, what forces are going to be acting on that block? Well, let's draw the floor. The language of the question will tell us what forces are acting. Connor? Gravity. Gravity is always acting, assuming we're on Earth. So we'll label it down, call it Fg. Okay, what else? Normal force acting up, perpendicular to the surface. What do we know about Fn and Fg in this case? Sorry, hold that thought. What other forces are acting? Connor?
Sounds like you have a friction force.
What implies friction?
Rough floor.
A rough floor implies a force of friction. And force of friction is going to be acting which way? No, force of friction does not act up. It's the opposite way of whichever way this block is moving. Do we know which way the box is moving? We just know that it is moving with a constant velocity. So in order to determine which way friction is going, we have to decide which way this box is going. Do we care which way the box is going? Okay, let's say to the right then. So we'll add that in there too, kind of off to the side. If that's the way the box is moving, the friction's going which way? Going to the left. And then what is the last force being added here? Force applied. Force applied is which way? And in this case, we actually know, given a lot of the information we're given, we can say some things about these different forces. What can we say about FF and FA? Oh, we're going Fn and Fg? Sure, we can talk about Fn and Fg. How do you know Fn and Fg are the same? The object's not moving up or down, and there's nothing else pushing up or down. So Fn and Fg have to be the same. That's good.
And we know that Fa is bigger than FF because the box is moving at constant velocity.
Okay, so you said that V is constant. Let's look at what that means. If V is constant, what is the implication there? Okay, it's moving the same velocity. What does that tell us about other things that haven't been addressed in the question? Like acceleration, for example. If velocity is constant, what does that mean for acceleration?
0.
Acceleration is 0. So these three dots in a triangle mean therefore. So if V is constant, therefore A is 0. If acceleration is 0, what does that tell us about, I don't know, net force?
Net force is 0 because any number multiplied by 0 is 0.
Okay. We know F net equals ma. If A is 0, F net has to be 0. Which means there is no net force acting on our object, which means all the forces have to be what? Sorry? Kind of. It's not the word that we... All the forces aren't the same as all of the other forces. Like Fg and Fn are the same, but that doesn't mean... We don't know that Fg and Fa have to be the same. So the forces aren't all the same, but all the forces are what, Angelina? They're all balanced. If all the forces are balanced, and we've balanced Fn with Fg, we know those two are the same. If F net equals 0, what other two forces must be the same?
not moving.
No, it is moving. It's moving with constant velocity, which means there's no acceleration, which means there's no net force, but it's still moving. Which means what has to be the same? The force of friction and the applied force that you're giving it have to balance out. Sorry? It was started moving at some point in the past. And then you just keep the forces equal, and then it will continue to move. Because we know where is what we know? An object in motion will stay in motion, and an object at rest will stay at rest unless acted on by a net force. So the box is moving. It is going to continue to move unless we allow a net force to act on it. You want me to bring up that motion applet again?
No, I get it.
Right. So we don't address how it started moving at some point in the past. At some point in the past, to get this thing moving, FA would have to be bigger than FF. That would cause an acceleration, bringing our velocity up from 0 to some positive value, yeah? Not if you agree with what I just said. Luis, you follow what I'm saying?
No.
Okay. I have a box. My box is not moving. Okay, box is not moving. I could push on the box, I'll go towards you. So people can kind of see from the side. You know what? No, I'll go this way. So I push, nothing's happening. I'm pushing, nothing's happening. I'm pushing, nothing's happening. What? Oh. Why is nothing happening?
Because the applied force is there's less applied force than the friction force. It's not balanced.
Well, I'm not pushing with enough force to break friction.
Yeah.
The whole time I'm pushing here, friction is matching me. Friction is always going to be equal to what I'm applying until this thing starts moving. So there's not more friction force, it's the same. It's always the same and it's building up to some value. Because it can't be bigger than what I'm pushing, because if it was bigger than what I was pushing, I would push and the box would fly that way. And that doesn't happen. So friction has to be equal to what I'm giving it, right? Eventually I will break friction and this thing will start to accelerate. But as you saw in the applet that most of you did, and some of you perhaps didn't do, but I asked you to do over the weekend, so hopefully you did, was that as you crank up your applied force, eventually you're going to break the force of friction that's keeping this thing static, and then friction is going to drop. We'll look at that when we actually get to friction and how we calculate it in more detail.
I think that's related to the inertia, because when the object is moving, it's easier to the object to continue moving.
Not exclusively. It's related to the materials that, when we get to friction, we'll talk about it in more detail. But if I keep pushing with that same force, the box is going to accelerate. But if I only push at, once I get this thing moving, if I push with the same, that friction's opposing me, this thing's not going to accelerate, it's just going to continue moving. If I want it to accelerate, I have to push harder than friction's pushing back on me. So you can have an object that's moving with no acceleration, and that means that once it's moving, these forces are still now come, these forces now come into balance, keeping this thing moving at a constant rate. Does that help at all? Okay. This is the free body diagram for this box. As far as we're told, there's nothing else acting. So the next one, a hockey player glides on frictionless ice at a constant velocity. What's acting on our dude? Or dudette? Yeah. Gravity. Hold on, one at a time. So I've got Fg. I hear a normal force from Luis. What else?
Why? Because
What do we know about
Oh, it's right.
the hockey player? They're gliding. They're gliding on frictionless ice at constant velocity. So again, let's label, off to the side here, we're going to label velocity. Which way is?
Right.
Sure, okay, we don't know which way, so let's say the right. So we know here that v equals some constant value. If v is constant, acceleration is going to be, which means F net is also 0. Frictionless ice means there's nothing.
So FF is 0.
So there is no FF. Yep. I'm not going to draw force of friction on here. We're told it's frictionless. And if there is no friction and F net is 0, can I have an applied force? No. And I think part of what we're getting confused about, maybe not confused, but part of the thing that you're trying to take into account is how could you possibly have a hockey player gliding on the ice having never had any force applied to it? And that's not what I'm saying. I'm saying right now there is no applied force on our hockey player. Could there have been an applied force earlier? Yeah, in fact there'd have to have been. I, who don't skate, might have been standing, at the bench and I push. The skater is now, there was one applied force, some point back in time, to get the hockey player moving, but now the hockey player is gliding on a frictionless surface, and unless something else acts, you will glide forever. We know that's not totally true because ice isn't completely frictionless. It's nearly frictionless, but it's not. So, like if you went skating and you got a solid push, eventually you would stop. But sorry?
Material that have no friction, like frictionless.
There are a few that come very, very close. One of them is, so there's a particular kind of jet fuel that is used in a plane called the SR-71 Blackbird. How many of you have heard of this plane? Not the bird, but the plane. So it was a spy plane that was used in World War II. It was very, very fast. It's large. It's made of titanium, so it's heavy. It needed to be made of titanium to survive the speeds at which this thing flew at. But when it flew at the speeds that it was designed to fly at, the thing would heat up and expand. So the plane itself, and I'll get to the point of all of this, the plane itself was built so that the pieces of metal, when the thing wasn't moving, were loose. So that at speed, it would fly like Mach 3.5. Maybe even Mach 4, I can't remember, it's like 3.5. So that at those speeds, the titanium would heat up, expand, and then the plane would fit together properly at speed. What that means was when the plane was sitting on the tarmac, it would leak fuel. And so there was a limited amount of time that they had between they fill up fuel and then they got to get the plane in the air because otherwise the fuel is just going to leak out of the plane. The fuel that they used in the Blackbird had such a low, we call it, we'll get to it, but we'll call it a coefficient of friction. It's the thing that governs how much friction is between two surfaces. The fuel had such a low value for friction that if there was fuel between the tire of the plane and the ground, or the tires of the plane and the ground, you could grab the nose of the plane and just give it a little push and the plane would go sliding across the floor. Because mass certainly does apply, but if the coefficient of friction is actually 0, if there actually is no friction, it doesn't matter what the mass of the object is, you can push it. So if you can drop friction, in this case, using this jet fuel, it doesn't matter what the mass of the object is, you can still push it. So there are objects out there that have very low coefficients of friction, and for certain times, we can say ice is practically frictionless because for a window of time, I give you a push on the ice, you're going to go and it's going to look like you have constant velocity. Practically speaking, if I push you on the ice, there's a bunch of things acting. The air that is in front of you, if I pushed you, we go to MRC, I push you on the ice, you're going to feel a little bit of wind. The air is going to contribute to you slowing down. But if I shoved you in a vacuum chamber and pushed you, you'd go a little bit further because in a vacuum chamber there's no air. But there is still going to be a tiny amount of friction between the ice and the steel because ice is going to give a little bit, you're going to dig in. There's a lot of stuff that's actually acting when we're talking about hockey players on ice. But for the sake of Physics 11, we got to start somewhere. And so if I tell you the thing is actually frictionless, you've got to remove from your head your own experiences with an ice surface and say, okay, frictionless implies this, which implies this, which implies this. So technically speaking, this skater would never actually stop, which I know is not how things actually go, which means how things actually go is more complicated. But for the sake of this, that's our free body diagram. Fn and Fg. For large portions of what we do, especially since I tell you that there is no constant velocity, we also have to assume that there is no air acting on this person, which means this hockey player is playing in a vacuum, which would be weird.
So wouldn't that cause like problems when they're filling up the jet, and if it leaks, they couldn't necessarily take off because the plane would slip? Or
That brings an interesting question. What's causing the plane to come up to speed?
the jets?
The jets. So it has nothing to do with the wheels.
Right, but
The jet engines don't spin the wheels on a plane.
no, but you have your wheels. You have,
Does it matter if they're rolling or sliding? They have nothing. The wheels have not on a plane. The wheels have nothing to do with propelling the thing forward.
Right.
It's
But couldn't that, because you haven't taken off yet, let's say you're going a really low speed before you're like going faster.
Carry on.
But
Yep.
what if your wheels slip and your engines are fine, they're only necessarily going in
Like when you're talking, like when it's taxiing from the hangar to the runway. Like if the thing has to turn, you're right, it has a problem.
not
But
quite.
if it doesn't have to turn, why is slipping a problem?
If it's not, I'm just saying, if it tilted, let's say you have a little bit of wind, the wind catches the plane, and the plane tilts a little bit to the left. on
Okay,
the
you're
side.
right.
So
Now
it
you've got a
has to-
problem.
Yeah.
Yeah. Yeah. Now you've got a problem.
Yeah, see?
Where, I mean, you'd have to look into where the planes actually, where the fuel tanks actually are. They're on the back of the plane. So the front's not going to be a huge issue. They're not near the landing gear unless you have a slick created. There's other, there's more to it than that. But you're right, yes. If for certain very specific circumstances, they had problems. And the reason I tell you this story is because they actually had problems getting the thing back into the hangar. It wasn't out that was the problem, it was back in. Because they got the thing back in, but because of the slick on the floor, the plane kept sliding and actually crumpled into the end of the hangar. They couldn't actually stop it because planes aren't built with brakes because those wheels, planes do have brakes, but because the frictionlessness of not that kind of brakes.
By the way, a question that is not related to that technically, but how a plane that is like Mach 3.5 could stop, like it wouldn't take so long to increase speed and then take crash, like
What's the question?
how a plane that is around Mach 3.5 could stop, like
How does it stop? Like when?
yeah, no, like how it stops because it's too fast, or the time to stop is not that long.
I don't understand the question. I mean, you just shut the engines off. The thing's going to stop.
Oh, but
Air resistance is going to push the plane. Is going to slow the plane down.
okay.
Just start gliding.
It'll just become a glider, and at that point, air resistance is going to cause the thing to slow down. Air resistance really only comes into effect for objects that we look at that are moving very, very quickly, or very, very large, or if the air itself is moving very, very quickly. Like if you're out hunting and you fire a bullet into the forest. You have to acknowledge it to a degree, but you're only talking about, well, you only have to really acknowledge air resistance if you're shooting like over kilometers. A couple hundred yards doesn't necessarily impact it. So air resistance is, like I said, complicated. Yeah, again, over kilometers. Assuming you believe the Earth isn't flat. Okay, here's what I want you guys to here's what I want you guys to do. Should we do a couple more together, or are we good?
I think we're okay. We get the concept.
I'm not sure you do, but we'll try it.
Whoa!
Okay, so let's do a couple of these. A book is at rest on a tabletop. Talk to me. What's going on here? Free body diagram this. We've got the table. We've got the book. What forces are acting on the table, or what forces are acting on the book, rather? The book that's at rest on the tabletop. Gravity and normal. Fg down, Fn up. And what do you know about those two? They got to be equal. Cool. No other forces acting on that thing. Thing's at rest. And we're not told that there's a push anywhere. Right. F net is 0. For the sake of the extra stuff that I did over here in pink, not technically part of my free body diagram. I was doing the pink. I was adding for our discussion about why things were the way they were. Yes, Naya.
Those lines that you're drawing on it, that represents the sky.
Yeah.
But at the top, there's the ET2 line.
So in geometry, you guys do less geometry in math than you did before. Like if I were drawing a square, don't draw what I'm about to draw. Just I'm doing it because that's where I have space. A square, we know the squares have all the same side lengths, right? That's the definition of a square. Well, it's not the only part of the definition of a square. All the sides are the same length and the corners meet at right angles. We demonstrate that this thing's a square by putting the 90 there and by putting individual lines to represent that this thing's, all of those are the same. What if, though, I had a rectangle? I know these two are the same. These opposite ones aren't the same as these two, but they're the same as each other. So I just do 2 marks instead of 1. So it's the same thing I did over here. The 2 marked ones are equal to each other. The single marked ones are equal to each other. I'm just borrowing that notation. Number 2, a girl sits on a swing that is attached to the frame by 2 ropes. So in this case, yes, we've got 2 ropes. Ropes suggest now that we've got tension. And there's 2 of them, so I'm going to need 2 tension forces, an Ft1 and an Ft2. We're just going to keep adding subscripts. So let's draw this thing. We're going to approximate the girl on a swing as a block. There's our girl on the swing. What forces are acting on girl on swing? Gravity, straight down.
T1 and T2 are the same.
That's not on the girl. That's on the swing.
Okay, so if we've got a girl. Oh, sorry, where's my mouse? There's my mouse. Okay, so if that's our girl, there's the seat. What other force is acting on the girl? We're going to have a normal force. She's on a surface. It's a normal force. So where are these 2 tension forces going to get drawn?
It depends on where the ropes are.
Typically, where are the ropes going to be on a swing? So I'm going to have a force. I should draw it in pink. I'm going to have a force up here. And I have a force up here. I'll call this one Ft1 and this one Ft2. Tension would have to go up. Because what else would be holding her upwards? Is that what Zaid was saying? Kind of.
Would be like the gravity force plus the the weight of the girl.
So if I call this FG girl, FG girl is the weight of the girl. There's one more FG that we haven't taken into account here. The weight of the swing seat. So I'm just going to draw it slightly off to the side. That's going to be FG swing. So you asked a good question. So FG girl is going to be equal to what other force here? Fn. The weight of the girl is going to be equal to the normal force acting up on her. She's not flying up into the air. She's not sinking downwards. So these two have to be balanced, Fn and Fg. Then these two tensions, what do these two tensions have to be? Added together is going to equal the swing seat and the girl. And assuming that they're placed at the same spot on the ends, the other thing that we can say about FT1 and FT2 is that they are equal. Because of how I've drawn it, because of where they're located, at this point we can assume they're equal. That is not always true.
Like we are balanced if the thing is crazy.
Depending, if she is perfectly centered and these things are exactly on either end, they're going to be equal. But if she's even slightly off center, you cannot assume that they're going to be equal. And this, I'll give you a preview of what's coming. In Physics 12, you're going to look at a concept called torque. And torque is going to determine whether or not these two are equal. But that's beyond this course. Khalil.
Would tension also rely on where the rope is placed on top?
Not necessarily, no. Height doesn't matter, but the angle they're at is what is going to be more important. If they're spread apart, there's going to be a difference in tension. But if one is attached, like if the roof is offset, that's not going to change the downward, assuming they're both straight up and down. Okay, number 3. I've got an egg free falling from a nest in a tree, and we are told to neglect or ignore air resistance. So I've got an egg. What's acting on my egg? Gravity. Anything else? Someone say either yes or no.
Yes.
Sorry? Who said no? Angelina said no? Oh, you said yes? So then what other forces are acting? So then no, there's no other forces acting. So yes or no. Are there other forces acting? Yes or no? No, there are no other forces acting. We're told to ignore air resistance, and this thing's in free fall. If I'm ignoring air resistance, the only thing acting is gravity. We're done. Okay. A plane flies at constant velocity. Let's draw our plane. There's my plane. We're told a few things here. There's a note. There will be an applied force generated by the engines as well as a lift force provided by the wings and air resistance too. So, let's label all of these things. What's acting on our plane? Gravity. What else is acting on the plane? There has to be a lift force because the plane's not falling out of the sky, but something's keeping it up. So there has to be a force of lift. Which direction is that going to be in? It's going to be up. We cannot call it a normal force because this thing's not on a surface. It's lift provided by the wings. What other forces are acting on this thing? There's an applied force from the engines, and Zaid, you just said? Air resistance. Air resistance is going to be which way? Okay, let's do it this way. Which way do you want the applied force from the engine to be? To the right? Okay. If this is my applied force from the engines, then air resistance has to be which way? The opposite way, yeah. And we'll call that F air. What can you tell me about these four forces? They have to be balanced. Good.
The F net is 0 because it's a constant velocity.
Correct. So then what other two forces must be balanced?
The F lift and the FG are balanced too.
Correct. Love it. Number 5, a rightward force is applied to a book in order to accelerate it across the desk.
So now F net's not 0 because it's a lift.
F net is not 0. Correct. So let's draw it. Here's my book. Here's my desk. What's acting? An applied force, a normal force, and gravity. Gravity acts which way? A normal force acts which way? So normal's which way? Straight up. The applied force, which way do you want it? Anything else? Typically for a book sliding on a desk, we're going to ignore air resistance. Yeah, friction's going to be an interesting one. Because it doesn't specify frictionless, friction's one that we can't assume that we're going to ignore. So friction's going to be which way? Against the force applied. And in this case, what do we know has to be true about these four forces? Sorry? You said at the beginning F net was not 0.
Oh yeah.
So can they be balanced?
No, so F A is bigger than F F.
Yes. FA is going to be larger than the force of friction. Are any forces here balanced? Fn and Fg are still going to be the same because this thing's not moving up or down. But in this case, Fa is going to be bigger than Ff because we're told that this thing's accelerating to the right. So there has to be a net force, which means these two cannot be balanced. Next one, number 6. Skydiver falling with a constant velocity. We could draw a block, but it's way more fun to draw people falling. So there's our skydiver falling with constant velocity. What's going to happen? Got air resistance which way? And gravity which way? And what do we know about those two? Do we know anything about those two? Sorry? If gravity were stronger, what would this person be doing?
Oh, flying most of the time.
F there is bigger because it's they're balanced.
Constant velocity means acceleration is 0, which means F net equals 0. If F net is 0, these things have to be balanced.
Yeah, I was thinking about like this situation like in a normal volume.
Well, this could be a real situation. It depends when you look at it.
Constant?
Yep. When I push you out of a plane, you're going to begin to fall, right? Which means you're going to be accelerating towards the ground at 9.8 meters per second squared. As you pick up speed, though, air resistance is going to get larger and larger and larger and larger.
What does that mean your final speed gets
Yes, exactly what that means. As you fly faster, air resistance pushes back on you harder. At the point where, assuming that there's no parachute, when you're at constant velocity, there's a term for this. Does anyone know the term? Brendan would, but he's not here. Sorry? The terminal velocity. And you will reach terminal velocity fairly quickly. What terminal velocity is depends on the shape in which you're holding yourself. If you're starfishing out, falling straight down, your terminal velocity is going to be pretty slow. If you tuck and point your head down, your terminal velocity is going to be much, much faster, but you're still going to eventually reach a maximum constant speed. And that's going to rapidly hit zero and you hit the ground, assuming you don't pull a parachute. But there is a terminal velocity here when these two are balanced and you're still falling. Air resistance is complicated.
Do you mean that, like, if there was like a smaller object, for example, I don't have any good ones in mind, but technically, no, but then technically something wouldn't necessarily like fall and like break into pieces and hit the ground.
Oh, it certainly would. Absolutely it would. Depending on the object, it could. You're combining. There's a few. You're combining too much.
Okay.
Strip away, and look just at what's happening here. So Manuel brings up an interesting example: the coin off an Empire State Building. Can you kill someone with a coin off an Empire State Building? Ignoring air resistance? Yeah, you bet. You can accelerate your coin to the point where it could fracture a skull. But terminal velocity is a thing, because coins don't actually fall straight down. As soon as you let them go, what are they going to start doing? They're going to start tumbling. The act of tumbling is going to dictate what the terminal velocity is going to be. And they've actually run the numbers. The worst you're going to do to someone is fracture their skull. You're not going to kill someone. And it doesn't actually matter how, and that's the beauty of it, it doesn't matter how tall a building is. Once the coin hits terminal velocity, that is going to be how fast it's going to hit the ground, regardless of whether you drop it from a kilometer up, or I think terminal velocity, we can reach it within, I think it's like 40 or 50 meters. A coin is going to reach terminal velocity. So it doesn't matter how high the coin is dropped from, you're still only going to fracture their skull. Now, if it's an anvil, we got a different story. Now the mass of the object is going to play a part of what happens at the bottom. Yeah.
A little bit off topic, but still comparing to the skydiver. When a human body falls all the way down, does it flat or bounce?
Depends on the surface beneath. There are lots of well, I shouldn't say lots. There are a number of examples where, like World War II, it happened a couple times. You bail out over Europe because a German just shot your plane down, and parachutes didn't deploy, and Allied pilot makes a 6-foot crater into a freshly plowed French field. If it wasn't freshly plowed, we have a problem. But because it was plowed nice and deep, because planting is going to happen, and he crawled out of the hole and he walked away. Because it's not about the fact that you were falling and now you're not. It's how quickly you come to zero. We can actually do those calculations right now, because you've got what you need. If I tell you the distance, he was going terminal velocity for a pilot, let's say, and he stops within 6 feet, so just under 2 meters. What's the acceleration on the body? You know, we could Google VI. VF is 0. The distance is just under 2 meters. You find A. I tell you the mass of the pilot. You find the force on his body. Like, it's relatively easy for you to do those calculations now, and we know it's been done. On concrete, you're going to bounce. On water, you're also probably going to bounce. Not a lot, because you're gooey. Yes, you're going to shadow all your bones, but you're probably still going to bounce. Not something I want to think about too much. Number 7. A football is moving upwards. It's after its peak, towards its peak after it's been booted, neglecting air resistance. What's going on with the football? Here's my football. Looks kind of like a potato. The booting has already happened. It's flying through the air. What forces are acting on our object, assuming we can ignore air resistance? Gravity. Straight down. Is anything else acting on our potato football thing?
No, you don't.
Why does it not have an applied force?
Because the applied force already happened.
It's already been booted. That happened at some point in the past. You open your eyes, the football's flying. What's going on? Does football have lift?
It's at its peak, so you don't know.
No, it's flying towards its peak.
Well, it depends on what point of it.
It's been kicked by a punter, so no, the thing doesn't have any lift. If it was a spiral thrown by a quarterback, there is a chance it would. A punter won't. A punter? I've never seen a punter spiral a kick. Interesting. Learn something new. I've never seen a punter spiral a kick. I've seen an Aussie Rules football player do it, but never a...
Aussie rules.
It's insane. The last one, a car is coasting to the right and slowing down. What's happening to the car? What are the forces acting on the car? There's got to be some sort of friction backwards. Well, where's the there's going to be friction, but where does it have to be? It's not going to be between the wheels. Where's the friction going to be? It's not going to be between the wheels and the ground. No. Where's friction going to be? It's not between, it's not on the ground.
On the tires.
Unless the only way this thing is, the only way friction acts between the tires and the road surface is if you slam on the brakes and lock them up. Or the car is sliding sideways. You make you're turning a corner too quickly and you slide off the road. Then friction is going to show up. But friction does not show up in a car coasting to a stop between the tire and the roadway. I heard it from up here. Where is it going to act? The axles, the gears, the bearings, all in the internal mechanism of the car. That's why oil is so important to have in a car, because you need that lubricant. But even with the lubricant, there is still going to be some friction there. That's why you put your hand on an engine, and it's part of the reason it's so hot. The other part is there's explosions going on in the cylinders, but the car itself is going to be warm because there's friction acting on all of those mechanical moving parts. So the friction here is within the mechanics of the car. And for an object that big, where else is friction going to be showing up? Or a type of friction? Is it just friction? The air is going to be pushing back against an object that big. Air is going to be involved somehow. Again, the slower you're going, the less it impacts it. But if you're in a semi-truck and you lose your brakes, air is certainly going to be pushing back against an object that big, that fast. So air is going to play some part. It's not going to be very big, but it's going to certainly act. What other forces are acting here? For a car on the roadway. You got gravity and your normal, and those two are going to be, those two have to be balanced. There you go. Relatively straightforward, yes? Okay. Flip the page. Here's what I want you to do. You're going to be playing with some free body diagrams here. These ones have all been drawn for you. For number 1, it says, for each of the following diagrams, determine the magnitude and the direction of the net force. For number 2, it says, use the missing information given for each diagram to fill in the missing blanks. And I want you to flip the page and I want you to do some of these.
How many?
I'm thinking odds. I'll leave the evens for you to practice if you want to play with them later. So 1, 3, 5, 7, and 9. The answers to these questions here can be found in here if you want to write these ones down. These are the answers to all, well, I guess there's technically 9, 10, 11 questions because there's 2 that have an A and a B. So write those down. Your answers for the ones that, well, for all of these ones are going to be found in there. So I want you to do all of those diagram ones, and I want you to do these 5. I guess technically 6 because 9 is A and B. Right now. On your market set giver.